Okay, let's talk about molecular geometry, which is known as VSEPR. Sometimes it'll say molecular geometry, or it'll say molecular shape, or just shape. So this is when we're looking at the valence shell electrons, and they're going to repel because electrons are negative. And so when they do this, they spread out to minimize the repulsion to get away from one another. So the procedure really quickly is, first you have to draw the Lewis structure. Then you have to count the number of atoms around the central atom. So make sure you're really careful about this word central. If it's a single or a multiple bond, like a double or a triple, they all count as one. Each non-bonding pair, which are your lone pairs, count as one pair around the central atom. And this arrangement determines the shape. So let's look at this chart. On the test, you will be given the first column, the second column, and the third column. So you don't need to memorize, you just need to know how to use this chart that we're going to refer back to. Here are some examples of what they look like in a 3D structure. Notice how on your chart it says triangular, but this says trigonal planar. Sometimes they just have different words for the same thing. You can use either one. That's fine. Okay, so let's look at how to do this. So our first example is CH2F2. And so we've already drawn this out. So what we're going to do is, after you draw it out, you're going to go ahead and you're going to look at that central atom. So the first thing is, count how many atoms are bonded to it. We've got 1, 2, 3, 4. So 4 atoms that are bonded to it. And then look to see if there's any lone pairs just on the carbon. Do you see any lone pairs? And a lone pair is going to be something like that, but just on the carbon atom. We don't, so this is 0. So then if you go back to your chart, on your chart you're going to see that, let's go ahead and go back there. Go back on our chart. We're going to see that 4 bonded atoms and 0 lone pairs is tetrahedral. So the shape of that molecule is tetrahedral. So this right here is going to be tetrahedral. Okay, let's look at the next one. COCl2. Again, we're going to look at the central atom. Here on the central atom, we've got 1, 2, 3 atoms that are bonded to it. Notice how we have a double bond, and that doesn't matter because we're counting the number of atoms. And then, are there any lone pairs on this, just this carbon, the central atom? The answer is no. So that's going to be a 3 and a 0. So if we go back to our chart, let's look for a 3, 0. And a 3, 0 is right here. It's triangular, or again, sometimes we call this trigonal planar. You'll see it both ways. So again, you can use either way on that one. Okay, let's go back to our next one. So this one's going to be triangular or trigonal planar. Okay, our next example is N2O, or dinitrogen monoxide. So again, let's look at this, and this is drawn a little bit differently. So if we were to draw it with our lines, here's what this one would look like. Okay. So now let's look at our central atom. How many atoms are bonded to the nitrogen? We've got 1, 2, so 2 atoms. And are there any lone pairs on the nitrogen? The answer is no, so this is 0. So again, if we look back on our chart for a 2, 0, we go back. Okay, our 2, 0 is right here. 2, 0. This one's linear. So that example is linear. So right here, this is going to be linear. Okay, let's look at our next example. This is NF3, or nitrogen trifluoride. So again, let's look at the nitrogen, the central atom. How many atoms are bonded to it? We've got 1, 2, 3, and we have 1 set of lone pairs right there. So that's a 3, 1. So again, let's look back on our chart. And if we go to a 3 and a 1, We're going right here to pyramidal. Now, sometimes they call this trigonal pyramidal instead of pyramidal, so just so you're aware of that as well. So on this one, we're going to say that it's our pyramidal. And that is how you figure out what this shape is, or they can call it molecular geometry. Okay, let's go to our next topic, which is molecular polarity. Now, you've already done bond polarity, which is when you take the electronegativity difference between just two atoms within a bond, and if it falls between a 0 and a 0.4, it's nonpolar. If it's between a 0.5 and a 1.7, it's polar, and 1.8 and above is ionic. So with molecular polarity, there's only two types we're going to talk about. We're going to talk about nonpolar, and nonpolar means that there's no lone pairs in the central atom, and all of the bonds have the same electronegativity difference. Another thing you can kind of talk about here is that they're going to have the same terminal atoms, if you want to look at it in a different way. Okay, so some examples here are carbon dioxide, methane, and carbon tetrachloride. So again, we have to draw these out. So I'm just going to hurry and draw these out so you can kind of see what I'm talking about. So this is carbon dioxide. Again, what you're going to look at is that central atom. So right here, we're going to look at the carbon. First question is, are there any lone pairs on the central atom? The answer is no. So then the second thing you have to ask is, do all of the bonds have the same electronegativity? Or another way to say that is, do they have the same terminal atoms? So oxygen and oxygen are the same. So therefore, this would be a polar molecule. Okay, the next one we're going to look at is methane, which is CH4. If we draw this one out, here's what it looks like. Okay, there we go. Again, you're going to look at that central atom. First question, does it have any lone pairs? The carbon does not. Then look at the terminal atoms. Are they all the same? The answer is yes. So that bond between carbon and hydrogen, this direction, this direction, this direction, and this direction are all the same. So therefore, it's nonpolar. Okay, our last example is carbon tetrachloride. So let's go ahead and draw this one. Nope, you can't see that color. Let's choose a different color. So there's your carbon and your chlorines. Oops. Okay, so once again, let's look at our central atom. Here's carbon. Does it have any lone pairs? The answer is no. And do they have all the same terminal atoms? And the answer is yes. There's chlorine for all 4 terminal atoms. So therefore, that's an example of a nonpolar molecule. Okay, let's look at our next type of molecular polarity, which is polar. Polar is when it's non-symmetrical. So you have to remember that when we're talking about this, we're talking about it in terms of 3D. So it's really hard to visualize in a 2D world as far as paper and pencil. But if you look at a molecule or think about it in 3D, then it makes a lot more sense. So on the polar, it's going to be just the opposite of the nonpolar. You're going to have a lone pair or pairs on the central atom that will automatically make it polar because those lone pairs decrease your bond angle. Or the bonds could have a different electronegativity, which means that you're going to have different terminal atoms. So we're dealing with different terminal atoms here. Okay, so let's go ahead and draw out ammonia. So ammonia, we have our nitrogen and our hydrogen. Okay, so let's look at our central atom here of the nitrogen. First question, does it have a lone pair or pairs in the central atom? The answer is yes. It's right there. It's our lone pair right there. So automatically this is going to be a polar molecule. And then the bonds, are the bonds different? No, they're all the same, but it can either be just a lone pair on the central atom or different. So that one's polar. So if we go back to look at these 4 examples that we did with molecular shape, let's see whether or not we think they are polar or nonpolar. So in this first example, CH2F2, we look right here. Does the carbon have lone pairs? The answer is no. Do we have all the same terminal atoms? The answer is no. So this would be a polar molecule because the terminal atoms are not the same. Let's look at this one. Here's our carbon. Does it have any lone pairs? The answer is no. What about the terminal atoms? Are they the same? We've got chlorine, oxygen, and chlorine. They are not the same. So this, again, would be an example of a polar molecule. Let's look at the next 2. So right here, let's look at our nitrogen. Does it have any lone pairs? The answer is no. Let's look at the terminal atoms. We have a nitrogen and an oxygen. Are they the same or different? They're different, so this would be an example of a polar molecule. Okay, last one, NF3. Let's look at the nitrogen. That central atom, does it have a lone pair? It does, so automatically this one's going to be polar. Even though the terminal atoms are the same, that lone pair makes that polar. Okay, I hope that helps. Let me know if you have any questions. Thanks. Bye.